Number 8 is a Hess's Law one. Again, they want us to take these 3 reactions and add them up to this one. So if I look for CH4, CH4 is in the very first reaction, but it's on the wrong side. So we're going to have to reverse reaction 1. So I'm going to make a note to myself, reverse. And right away, we know that that's going to give us a negative X for delta H. I look for O2. That's the one that's in more than one reaction, so I'm going to ignore it and leave it for later. CO2 is in reaction 2. It's on the correct side. It's a product, and it has 1 mole of it formed. I think that looks good. So I would say leave this one as it is. So we're going to keep it as Y. And then water is in the third reaction. It is on the correct side. It's a product, just like it should be. But we need this to be 2. So everything in here has to be doubled. And so for this one, we're going to double it. And that's going to remind us that delta H is now 2Z instead. Now, you got to be a little bit careful in just adding these things up. I mean, I do see an answer that looks correct. It looks to me like D would add those up well. It is worth taking a moment and making sure that things cancel, that you didn't miss something like that. But I would say D is probably the correct answer. In number 9, they want us to predict what delta S will be. You remember that is entropy, and since you have one thing becoming 2 moles of products on the other side, plus you have a solids creating a gas, definitely there is increasing entropy. So I think delta S is likely to be positive here, but we have to come up with a reason to decide between A and B. The products are more disordered than the reactants. That is true, they are more disordered. The products are less ordered than the reactants. Yep, this is the question where these two things mean exactly the same thing. I apologize for this typo here. People have talked to me about it. If that strikes you as meaning the same thing, it is true. So you could put either one in on WebAssign, or we will correct WebAssign. I will say this is a lesson for us when we're writing about this in free response. Don't use more disordered. It's a double negative thing. Talk about things being more or less ordered and leave it at that. So A or B works here, and if not on WebAssign, I'll get it fixed afterwards. If we go on to number 10, based on the information given in the table below, what is delta H for this reaction? Ooh, it's a bond enthalpy 1. So you remember we set it up so that the bond's broken. We add up those bond enthalpies and the bond's formed. And then we add those up, and we are going to subtract this number from that number and get the delta H. Well, in the reaction, I believe that's an H2 right there. So an HH bond is in this thing, but there's 2 of them because of the stoichiometry. If it's 500 for each one, I'm going to say 1,000 joules to break those bonds. And then there's 1 O2 here, so there's 1 OO bond, that's 500. That means that we have to put in 1,500 joules of energy in order to break the bonds. On the water side, if you draw water out right, you have 2 OH bonds in each water, but there are 2 waters. That's why I have 4 OH bonds. And 4 OH bonds is 2,000 joules. So I have 2,000 joules on this side. And when I subtract those 2, I'm going to get negative 500. The answer should be B. Number 11 is asking us about a reaction that is thermodynamically favored at 298 and becomes unfavored at higher temperatures. So this is seeming awfully familiar. This looks exactly like one we've done before. If that's true, you got to think through a Gibbs-Helmholtz equation. So this is a reaction that it becomes unfavored at high temperatures. If you increase the temperature, it becomes unfavored, which tells you the T delta S term is unfavorable, which tells you that delta S is a negative delta S, as in the reactants becoming more ordered. Maybe a little bit like this one. It's unfavorable entropically, so delta S is positive. Now, delta H has to be favorable, just like we saw before, because if these two were both unfavorable, you could never have a spontaneous reaction. So they can't both be unfavorable. So this must be favorable. It's negative. It's exothermic. And now we know the signs. Delta H is negative. Delta S is negative. So the answer is A. Boy, that looks very much like one we've done before. But I believe the answer is A. On to 12. Which of the following will be true when a pure substance in a liquid phase freezes spontaneously? Well, I'm going to write out a couple of things here. Here's one. Whenever you have a phase change, it's helpful to think about what's actually going on. And the reason I'm writing liquid water going to solid, because that's freezing, is because I want to think about particles in phase changes. In the liquid state, the particles are moving with a moderate amount of velocity. They have relatively high kinetic energy compared to in the solid. They have essentially all they're doing is vibrating, right? In order for this to occur, that means they have to lose that kinetic energy. That means it's going to be exothermic, right? Because it has to release that energy to get down to a less wiggly state. So delta H right there we know is negative. As far as delta S goes, though, remember delta S has to do with order, and things are becoming more ordered here. The particles are in a crystal structure, so delta S is unfavorable. It's more ordered, and so delta S will also be negative. Now you might wonder about delta G. Well, they said up here it freezes spontaneously. That tells us delta G has to be negative as well. So therefore, all three are negative. It looks to me like the answer is B.